So previously we came up with a limit definition for the slope of the tangent line. And that limit definition looks like this. So let's just say recall the slope of the tangent is equal to, and it's the limit of this special difference quotient where we had f of x minus f of a over x minus a, right? And the whole idea is we have the graph of a function, so let's say this is our function, y equals f of x, and we have a fixed point right here, which I'm going to call a, and then we want to find the slope of this line that is tangent to the curve at that point, right? So the slope of this line is what we're indicating by the symbol m sub tan, right? So the abbreviation TAN stands for tangent, and of course we're using m because we're still talking about a slope, and we typically use m to represent a slope, right? And this is pretty fun. We did an example, and it worked out that we required using some of our limit operations from previous sections, right? So what we're going to do in this video is come up with a slightly different form of this definition. So it's an alternative definition. They're equivalent in terms of the amount of algebra you might have to use, but this alternative form lends itself for a next big idea that we have to develop, right? So what is this form? Well, just to remind you of where this came from, we started with graph of a function, and we had 2 points on that function, and the first x value, this was fixed. This is the point at which we want the tangent line, so that was fixed. And then we had our second point being a variable, right? And what we're going to do now is, instead of using a and then a different letter x, I'm going to use another letter. We're going to call it h, and this is how it all relates. So the way, for instance, the number line is labeled, where I have x further to the right than I have a, then it means x would have to be bigger than a, right? So the further you go to the right, the larger the number. Well, if x is bigger than a, then I can write x as a plus some positive quantity, right? So if I take this number and then I essentially add this positive, this difference right here, then I will end up with this number. And I'm going to call that positive difference h. Sometimes it's called delta x, right? So it might be something like this. For now, we're just going to use h, right? So essentially what I'm going to do is, with this single equation, I am going to convert this limit into an equivalent limit that looks a little bit different, but it gives us exactly the same information, right? So let's do that. So let's say, let x equals a plus h, right? Well, if x is a plus h, then I could actually solve for h and say that x minus a is equal to h, right? So how does that help? Well, let's look at our formula. So we have an x here, and I'm going to replace that x with this quantity, right? So that's going to go where the x is. And then also look in the denominator. I have an expression x minus a, but I have the exact same expression here, and that's just my h. So the h is going to go where the x minus a is. The a plus h is going to go where the x is, and then I have to figure out what happens as x approaches a, right? So look at this equation here. So let me write it this way. So h is equal to x minus a. So if I were to take the limit of this side, right? So in fact, let's not even write it as a limit, but just realize what happens is as x gets closer and closer to a, h gets closer and closer to 0. Because like for instance, if I plug a into the right hand side, I would have 0. So again, we can convert every aspect of it and say this. So as x gets closer and closer to a, h will get closer and closer to 0. So this now, this part of my limit will be replaced with this, right? So pretty much everything now that previously had the variable x now has this other letter h, right? So notice the three things that I have highlighted here, they all involve the letter x. But with this little change, I can change all three things so that they now involve the letter h. And then we'll get this alternative definition for the slope of the tangent line. So therefore, slope of the tangent line is now, so it's still a limit, that's not going to change, right? Our definition for the slope of the tangent line will always involve a limit. So it's a limit, but now instead of writing x approaching a, I'm going to write h approaching 0. So I'll have this part. I'll still have my f, but then instead of writing x, I'm going to write the quantity a plus h. So it looks like that. And then the f of a is just a constant, so that stays, so minus f of a. And then in the denominator now, the quantity x minus a just gets replaced with the letter h, right? And again, this is the definition, an alternative definition for the slope of the tangent line, provided the limit exists, right? So provided the limit exists. All right. So just with a slight change in perspective and a slight, almost you could almost say change of variables, where we're switching from x's to h. But the h is sometimes not really referred to as a variable. It's more of like a parameter, and it controls how close we are to this fixed point A. And as h gets smaller and smaller, then you get closer and closer to A, right? So it is equivalent to this, it's just a different way of writing it down. So let's do a couple examples illustrating how we can use this as opposed to using our initial formula, right? And what I'll do with these examples, we'll do two things. We'll find the slope of the tangent line at a specific point using our limit, and then we'll find the equation of the tangent line at that specific point. All right, so let's take a look at two examples we have. So the first one, here is our function. I'm going to take a simple square root function. So let's just say it's the square root of x plus 2. And I want the a value to be, in this case, in other words, the value of x at which I want the tangent line. Let's say that x is equal to 7, right? And we're going to ask two things. What is the slope of the tangent? And what is the equation of the tangent? And it's important to remember the difference between the slope of a line versus the equation of the line, right? So let's answer these two. And again, what we're going to use now is this alternative definition. So I'll leave it right there so we can set it up. Now, it's really important how you interpret this, right? It's really key as to how we interpret this. So let's set it up. So the slope of the tangent to this function at this point, it's now going to be the limit as h approaches 0 of, well, again, let me write it down symbolically. It's our f evaluated at 7 plus h, and then minus f of 7, and then this is all over h, right? So that's how it's set up symbolically. Now let's go ahead and evaluate, right? So again, what this means is like whatever is inside the parentheses, when I go to evaluate this, I replace our variable x with the expression 7 plus h. So it looks a little, almost cumbersome when we set it up, but trust me, it will work out, right? So we'll have the square root, so wherever there's the x, put the quantity 7 plus h, and then I also have a plus 2 there, right? So that's the first term in the numerator. The second term, just like our first limit definition, always it ends up being a constant right here. So plug 7 in, that's the square root of 9, which is 3, and then this is all over h. All right. Now, if we then change our, if we now focus on evaluating this limit, the first thing we will do is try to see, well, what happens if I take the limit of the numerator? So if I take the limit of the numerator as h approaches 0, right? Well, we're going to try to do it algebraically and by plugging in h equals 0. So this is the square root of 7 plus 2. That's the square root of 9, and then minus 3. So that's 3 minus 3, so that's 0, right? So the numerator approaches 0, and so does the denominator. So again, the limit as h approaches 0 of h, that's also 0 if I plug in 0. So once again, it's an indeterminate form, and it is not a coincidence. These limit definitions always start out as an indeterminate form, and then we have to use one of our algebraic tricks, if you will, to evaluate it. Right? And the trick that's used when you have a radical is to rationalize, right? So we're going to rationalize this. So by rationalizing, and hopefully you remember what that means, we're going to multiply this difference quotient. It's still a difference quotient, it's just that the difference in the denominator simplifies quite a bit. But multiply this difference quotient by the conjugate of the numerator. So it looks a bit bulky when we write it down, but let's do it carefully. So rewrite the difference quotient. So 7 plus h plus 2 minus 3 over h, and then multiply the top and the bottom by this other quantity. The same root, 7 plus h plus 2, but instead of minus 3, change the sign to a plus 3. That's the definition of the conjugate. You change the operation between the two terms. You don't change anything under the radical, you just change the sign between the two terms. And since we multiply the top by that quantity, we have to multiply the bottom by the same quantity. So we got 7 plus h plus 2 plus 3. All right? So yes, it does look a big mess, but why do we do this? Because now in the numerator, we have this pattern. We have the pattern a minus b times a plus b. And when you expand this, this is your difference of two squares. And that's what will happen. So if I go to simplify the numerator, that radical by itself means that the square root goes away, right? So I just have the quantities 7 plus h plus 2. The middle terms will cancel out because one will be a positive 3 times that radical. The other one will be a minus 3 times the same radical. So because they have opposite signs, they'll cancel out. And then the last term is going to be a negative 3 times a positive 3. So that's a minus 9. So that's what happens in the numerator. In the denominator, there's not much we can do. I'm just going to keep it completely factored like this. I'm not even going to distribute the h, because if you look closely in the numerator, something very, very significant is going to happen. Right? So we don't need to do any sort of expansion in the denominator, but look at the numerator. The 9 cancels out because in parentheses I have 7 plus 2, and then here I have a minus 9, so all we're left with is just an h. So it's the limit as h approaches 0. And so I have h in the numerator and then a factor of h in the denominator. And that's what you always want to see in this process. You want to see a factor that's common in the numerator and in the denominator. So now we can reduce the fraction. Just be careful when you reduce, and it happened earlier when we dealt with limits. Just remember that there is a factor of 1 that's left, right? So we're going to have a 1 in the numerator, right? And then we have the root of 7 plus h plus 2, so that's all under the radical, and then we have a plus 3, right? And now we can plug 0 in again, and this time we won't get something indeterminate. We will get an actual number. The numerator is 1. The denominator gives me root 9, which is 3, plus another 3. So the slope of the tangent line to this function at this point is 1/6, right? And again, just as a reminder, here's our function, the square root of x plus 2, and we wanted it at the point where x is equal to 7, right? Right, so again, just as a reminder, here's our function, y equals the square root of x plus 2 at x equals 7. The slope of the tangent line is 1/6, right? So that's the slope. But how do we find the equation of the tangent line? Well, we know the x value. That means we automatically know the y value. When x is equal to 7, y is equal to 3. So we have the point, this is the point that the tangent line passes through. And this is its slope. So we can use the point-slope equation of a line, right? And I always tend to use the point-slope. If you prefer to use the slope-intercept, feel free. Again, you have a choice, right? So using the point-slope equation of a line, then that will give us the equation of the tangent line, because we now have the slope of the tangent line. So it's y minus the y value, which is 3, and then that's equal to 1/6 of the quantity x minus the x value, right? So this is an equation. Now, if you wanted to put this equation in the y equals mx plus b form, you could, right? So you can start with the point slope and then convert it to the y equals mx plus b, depending on what the what your instructions are in a particular problem. But here is the rest of the process. So distribute the 1/6. So we have 1/6 x minus 7 over 6. Add 3 to both sides. So 1/6 x minus 7/6. Now 3 over 1 is the same as 18 over 6. So just getting that common denominator so I can add these two fractions. So here is the slope-intercept form of the equation of the tangent line. So 1/6 x negative 7 plus 18 gives me a positive 11 over 6, right? So all of these are equivalent, so depending on what your instructions are, you could leave it in this form, or you could leave it in the y equals mx plus b form. All right, so that's what it looks like when you have like root functions, right? So you end up using, you end up rationalizing quite a bit. Let's do a second example to illustrate this. And again, let's take a different type of function so you can see what all sorts of, algebra techniques you'll have to use, and it depends on the function. So let's say now my function is, let's say it's 2 over x. And we want the slope of the tangent line when x is equal to, let's say, 3, right? Same question. What is the slope? So let's just use our mtan notation there. So what is the slope of the tangent line? And then also let's go ahead and find the equation. More practice with the equation, right? Okay, well, let's set this up using this alternative limit definition. So the slope of the tangent is the limit as h approaches 0. Again, let me write it down symbolically. This is now my a. This is the value, the point at which, well, the x value at which we want the tangent line to be. So it's f of a plus h minus f of a all over h, right? And then we have this. So when we substitute into the function now, replace the x with the entire quantity 3 plus h. That will give you the first term. And for the second term, that's going to be numeric. Replace the x with the number 3. So it looks like this. And we have 2 over the quantity 3 plus h minus 2 over 3, and then this is all over h. Now, whenever you have fractions within fractions, they sometimes call them complex fractions, whatever you want to call them. The whole idea is to simplify, right? We don't consider this expression simplified. And let's do it in stages so we don't get too overwhelmed with the algebra, but it's key that we understand all the steps here. So to do this, let's get the common denominator, because we're taking the difference of two fractions. In order to do that, we need the common denominator. So the common denominator in this case will be, and I'll keep it factored, as 3 plus h times 3. So what this means is I have to multiply the first fraction, top and bottom, by 3. So that makes this numerator 6. So I'll put that there. And then minus, and then for this one, I have to multiply the top and the bottom by the quantity 3 plus h. So then this will be 2 times the quantity 3 plus h. All right. So again, this is not completely simplified. Let's see all that we can do. So first, distribute the negative 2. So this is equal to 6 minus 6, and then minus 2h, and then that's all over the quantity 3 plus h times 3. All right. Well, we can definitely see what happens with the 6. Those terms cancel out, so we're left with a negative 2h in the numerator, and then at the bottom here, if you really wanted to, you could go ahead and distribute the 3. It's not vital, but if you do, it looks like this, 9 plus 3h. Right? We can't reduce this anymore. There are no common factors here. Don't be tempted to try and cancel out those h's. That won't work because h is not a factor of the 9. So that's the top part. So let me do that. So we're slowly getting this expression simplified. So the top part is negative 2h over 9 plus 3h, and then that's all divided by h, right? So let's do a little bit more algebra off to the side again. So maybe I'll use a different color here. So for this one, this is how you can interpret it. You literally have a fraction. So this is negative 2h over 9 plus 3h, and I'm literally going to write it as division. How often do we use the symbol anymore? But we're taking this fraction and dividing it by h. So I'm going to put the h here as h over 1. Think of it as a fraction, and then ask myself, well, how do I divide by a fraction? Well, you multiply by its reciprocal, right? So take the reciprocal and you multiply. So we have negative 2h over 9 plus 3h, and then what happens is there is that common factor again. This reduces, right? And then so all of this now reduces. There's still a negative 2 in the numerator, and then the denominator is 9 plus 3h. So I think we've finally got it to a point where once we've canceled out that common factor of h, then it means we're free to evaluate it again, right? So there is our simplified numerator and also simplified denominator like that. And if we now evaluate this as h approaches 0, we can plug 0 in, and we don't get a 0 in the bottom. We don't get a 0 in the numerator. It's no longer indeterminate. But what we have left is negative 2/9, right? So that is our slope. So again, to summarize what we just did, here's our function. It was 2 over x. Oh, not 2 over 3. 2 over x. And at x equals 3, we got that the slope of the tangent is negative 2/9, right? After a bit of algebra, we got it. This is our slope of the tangent line. Now let's find the equation. Anytime you have to find the equation of a line, whether it's a tangent line or some other line, you need a point and you need its slope. Well, we have half of the point, right? We have the x value, but we know how to find the y value. Plug it into your function. So your corresponding y value is 2/3. So the point that the tangent line passes through is 3, 2/3 with this slope. So then again, I will use my preferred point slope form. So using the point slope equation, let's write down the actual equation of the tangent line. And it's y minus the y value, which is 2/3. And that's equal to the slope, which is negative 2/9, times the quantity x minus your x value, so x minus 3. And again, if we wanted to, we could go ahead and express this in the slope-intercept form. So essentially solve for y, simplify what's on the right. So let's distribute the negative 2/9. So that's negative 2/9 x, and then plus 2/3, right? Because we have those two negatives there, and we're multiplying, and then add 2/3 to both sides, and we end up with negative 2/9 times x plus 4/3. And this is the equation of the tangent line. So this is the equation of tangent. Again, not to be confused with the slope of the tangent. So slope of tangent. All right. So there are a couple examples, again, illustrating this alternative form of the limit definition of the slope of the tangent line. Now, if you're not told which one to use, you essentially have a choice. But if the question says, find the slope of the tangent line using an appropriate limit definition, then your process is either going to look like what we did in the previous video or what we just completed in this video, right? But it's the idea of showing that we can use limits to compute this tangent line, right? So next video, we're going to take this idea and just keep building on it and building on it and building on it. So again, I know I keep saying that we're setting a foundation, but now we're starting to go up, right? So we're going to build this wonderful high rise, and the base, the foundation, it all starts with limits and these concepts, right? So see you then for our construction project.